Now we're back looking at our notes. We'll take our demonstration from the air track and relate it to this. So what's the relationship between the motion of an object and the net external force? So what is a net external force and how does it affect motion? How do you determine that net force? And then finally, how do you calculate the force required to bring an object into equilibrium? So obviously we need to define what equilibrium is, we need to define net external force and answer these. So to start off with, this is basically a leading series of questions that goes with the air track. What keeps an object moving? Well, we think a force does. Well, what makes it stop? A force makes it stop. What if friction never goes away, right? That's the world we live in. Friction never goes away. So there's always a force making things stop. Friction. Well, what if friction didn't exist? All of a sudden, the force that stops the motion is not there, and that allows us to discover the true nature of the true nature of an object's motion, which is to either stay at rest, or to stay in motion, or to travel in a straight line. So the only reason an object stops is because friction. If you remove friction, then an object would never stop moving. And you see that when you get on ice or something like that, if there's no friction on the ice, then how do you stop yourself from moving? It's very difficult to do. So forces make it move faster, make it move slower, or make it change direction. And without a force, you will continue to move, or you will stay at rest, and you will stay in that same direction. All right? So Newton's first law says an object at rest remains at rest, or an object continues in motion with constant velocity. So constant velocity means constant speed in a straight line, because velocity is both speed and direction. Unless the object experiences a net external force. What is a net external force? Well, a net external force is the sum of all the forces acting on it where there is a positive gain or one force is greater than the other in the system. So if I push with more force than gravity pushes, if I push with more force than friction pushes, then I have a net force and the object would move. So let's take a really quick free body diagram here. Say we have a car, and the car has a force of the motor, and that motor is, we'll give it 200 newtons. All right, now we have a force of friction. And let's say that force is 180 newtons. So because the motor is greater than the friction, the car has a net external force, which means the car will accelerate. Not only is it moving, it's moving faster and faster and faster. So Newton's first law is often referred to as the law of inertia. So we go back real quick and we say, what is the relationship between the motion of an object and the net external force? When you have a net external force, the object will actually accelerate and get faster and faster and faster. Not move or stay at rest, but move faster or slower or change its direction. You need to be careful about the way you think about that. Forces don't make things move, they make them move faster or slower or change the direction. It's the acceleration, right? All right, Newton's first law is often called the law of inertia. How do we determine the acceleration from a net force? We sum them up. So the net external force is the sum. We add them. Why did we spend all the time on vectors? Because if we want to get a net force, we need to add the vectors. Now vectors could go in the same direction. We just add them. Vectors could go in opposite direction. We subtract them. Vectors could be at 90 degrees, Pythagorean theorem, so forth. We could use even the component method. Okay? Think about a tug of war. I pull one way, someone else pulls the other. Those forces subtract against each other. If one group pulls with more force than the other, then there's a net external force. The object accelerates in that direction. How do you determine the net external force? You simply add the vectors. Of course, there's lots of ways to add vectors. Let's try to look at equilibrium and define that. So mass is a measurement of inertia, and we know that an object's inertia is proportional to its mass, and you should have seen that from the lab activity. that as the mass of an object goes up, the acceleration of that system would go down. So the bowling ball has more inertia because it's more mass, which means its acceleration is going to be lower under the same force. Objects in motion tend to stay in motion because the mass is proportional to an object's acceleration. So for example, seat belts. Your body wants to stay in motion, so we use a seat belt to attach you to a larger system. So you actually become part of the mass of the car. Now that you're part of this much larger mass, your acceleration would go down. So seat belts work with this because they attach you to a much larger mass in which your acceleration would then decrease. If you're not in a seat belt, then you're a small mass and you're separated from the system, and small masses have much greater acceleration. So in a collision, you would actually accelerate faster than the car. So if the car's moving and you accelerate faster than the car, you would actually get thrown out of the car. And that's what we've seen and heard stories about. Equilibrium. Equilibrium is an example of Newton's first law. This is when objects are in equilibrium. Equilibrium produces constant velocity, so we want to be careful about that. Remember, constant velocity doesn't get faster, doesn't get slower, and does not change direction. That system is in equilibrium. When you're in equilibrium, the forces all equal zero. So, if you're in a car going 50 miles per hour on cruise control, 50 miles per hour cruise control, you're going the same speed over and over and again. That means that all the forces on the car are balanced. So again, we have a car, and that car is going in this direction at constant velocity. So if this is 100 newtons, and I'm at constant velocity, that means my forces must total zero. So that means there's another force going this way, and 100 to make it total zero means I must have 100 going in the opposite direction. So, how did we calculate the force to find equilibrium? The force to bring an object into equilibrium is the same magnitude but opposite direction as the net force. Is this car moving? Well, it could be moving at the same speed, just not getting faster, not getting slower, and not changing its direction. That's one of the most missed things in this concept is a car moves at constant speed. Does it have any forces acting on it? Yes, it has forces. They're just all equal to zero when you add them together. The net force is zero. There could be hundreds of forces, but they all add together to equal zero. How do you find a force to bring a system into equilibrium? The force required to bring a system into equilibrium is equal in magnitude, but opposite in direction to the net force. Okay? All right, so we have a couple examples here. Start off with real quick. What is the net force in this system? You got 10 going up, 15 going down. It is simply 5 down. Add these. What do you do down here on this example? Those forces are at right angles. You'll have to Pythagorean theorem this set to find the resultant or net force. All right, once we solve these basic ones, then you got examples where we have the words and you got to draw them 70 newtons at 30 degrees. You got to find the components just like we've done with lots of the vectors. So I want you to give these a try and submit your work.